This lecture, we will study the analysis of stress, Cauchy's stress principle, and the stress vector. I recommend that you study the last video, the last lecture. There we talk about how is the influence of the normal vector to the small surface area delta S. Now, consider a body and a small volume delta V in this body. Around you see the point P and a small volume delta V. Now, here's the Earth, okay, that the delta P is a body force that acts on this volume delta V. The force, the weight is delta mg, is a vector. Now, consider a surface delta S. You see, you have a small body, just you cut this body, and then you analyze this area delta S, in which n is a normal vector to this delta S, as is shown here in this picture. Now, you see the area delta S. This is a normal vector to delta S, and here is a force. You see here, this T of n is called a stress vector, is defined like this. You see, this stress vector at P is a limit as delta S goes to 0 of delta F divided by delta S. Now, it's important to remark that the stress vector, the unit of stress vector, is force divided by area. That's important. Now, look, if we rotate S, it will change n. So if you change n, this stress vector will change. You see, the example that we did in the last video is very important for you to understand this. So when you rotate this delta S around point P, we see we have another normal vector, perpendicular to this surface area. So T is a function of n, and this is the limit as delta S goes to 0 of delta F, the force divided by area. This is stress vector at point P. Point P inside a small volume delta V. Now, you see, for a point P, there are many possibilities to have delta S and n. You see, so you see n here. You can rotate in several ways around the point P that you have different stress vector. Fortunately, this stress vector at the point P can be characterized if you give only 3 stress vector on the x1, x2 plane, x2, x3 plane, and x1, x3 plane. As I said before, fortunately, the stress vector components can be represented in the 3 planes, okay, as shown in this picture. So here is a normal vector that's called E1. Here is a normal vector E2, and this is a normal vector E3. Now, here I'll put a stress vector T here associated to E1. I'll put here. Here is a, you see, is a plane, and this x1, x3, in which E2 is a normal. So let's do this, okay? This is T, and this is associated to the normal vector E2, and finally, this is a T associated to the normal vector. Let's put here E1. See, this is E2, and this is E3. See, that's a normal vector, E1, E2, and E3. So the normal E1 is a normal vector to this surface over here. You see, this surface over here. This surface lies in the x2, x3 plane, in which E1 is perpendicular to the surface here. That surface over here, okay, that surface, it lies in the x1, x3 plane, in which E2 is a normal vector. And the last one, the surface here, okay, look, the surface lies in the x1, x2 plane, in which E3 is perpendicular to this surface. So you see TE1, TE2, TE3 are the components of the stress vector at the same point P. This is P, P, and P. You see, I just showed in different pictures just for you to understand what we are going to do. This vector over here, this vector is in the R3. So I can decompose this vector in the standard basis. So this TE1, that's right here, I'll write down over here. See, this TE1 is equal, now T1, E1 plus T2 of E1, E2 plus T3, E1, E3. Don't be confused, because look only at this stress here. You see, look only at this stress here. This is T, okay, of E1. You see, T of E1. You see, this vector here is in the space. The vector here doesn't belong to any plane here. So I can decompose in the three components here. Let's put E1 here just for you to understand. So this is U1, this is U1, and this is U1. The same, we can decompose T of E2. This is T of E2. You see, T, this here, I will project, okay, in these three axes. So this is T of, I'll put over here, T of E2. See? This will be, again, is equal. You see, look, T1, E1 plus T2, E2 plus T3, E3. Now, this is E2 This is E2, and this is E2. It's quite simple. Now, let's project this vector over here. This is stress vector. Okay? Now remember, this is not force. This is force divided by area. So T is equal T1 E1 plus T2 E2 plus T3 E3. See, now this is E3, 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 and E3. You see? Now, you can see here that we have 9 components. You see? 3 components here, 3 here, and 3 there. So each of the stress vector, okay, related to this unit vector here, it has 3 components. On the same idea, this stress vector here related to E2 is decomposed in 3 components. Likewise, T3. So this you have. Now, I can write this using a tensor notation. Don't forget, we are vector and tensor notation. So this is summation. You see, look, E1 is fixed. Okay, this is 1, 1, 2, 2, and 3, 3. So it can write here T, J, EJ. Now here is E1. You see? This is a summation. This is a dummy. Okay, now let's put the. Now, this one is T, J, EJ. Okay, doesn't matter. Now, put the J over here. Now here will be E2. E2. Here is TJ, EJ, you see? Now here will be E3, E3. You see? Now this is sum. J is dummy, okay? Now I can represent now an element of this just writing like this. Look, T, J, EJ, here I put EI. You see? This is TJEI because when I is equal 1, I decompose in this row over here. For I is equal 2 is E2. If for I is equal 3 is E3. So this is sum, this is dummy. You see? I is the free and J is the dummy. Now we can see, do you remember when we start learning about the notation, okay, we forget about the unit vectors and work only with this component over here. You see? This is a component over here. This component here I call sigma ij. I don't know, just to recall, okay? Just to remember. Do you remember when you have, for instance, a summation of, for instance, Vk Ek? For k is equal 1 to 3, this will be V1 E1 plus V2 E2 plus V3 E3. Do you remember that? This is a vector. This is a vector v. This is a vector v. This is equal vector v. And then for the notation, you just forget about the summation, forget about this, and the vector is vk, so the one free index. Exactly what we did here. So let's forget ej and work with the component sigma ij. These are called a stress, okay? This is stress sigma ij. This is tj ei. It's simply. Right? How many components do you have here? Do we have here? You have 9 components. So this is a matrix. You see? Now for the last video, if you rotate the x axis, okay? Now you're gonna have a similar matrix to that one. Okay? So this is what you call analysis of stress. So this is a matrix. This is elements of a matrix. This is a second order tensor. See? This is just the components of a second order tensor, or the elements of the matrix sigma ij. Now it's clear now how appeared the stress matrix. Okay? The stress matrix came from the stress vector, as we pointed out right here. Now, the stress tensor that we just saw, sigma ij. Now, you see, here is a summary what we did. So ti, ti, ti. So I is equal 1, 2, or 3, as we did before. So this is the stress vector associated to the normal vector E1. This is normal vector E2. This is normal vector E3. Now, if you project ti E1 for 1, 2, 3, project on this x, x1, x2, and x3, you just get sigma 1, 1, sigma 1, 2, and sigma 1, 3. Now let's do the same with ti E2. Now ti E2, let's project this vector on the R3. You see, there's a space R3. Now you have T1, you see, T1 E1 plus T2 E2 plus T3 is 3. This associated to the normal vector E2. What is going to write here? Let's write, this will be, you see, this is sigma 2, 2. Now, here and here. This is sigma 2, 1. You see, associated to x1. This is sigma 2, 3. You see, associated with the direction 3. The same we do for this first here. You see, ti associated to E3. So the unit normal vector in the x3 direction is E3. So here we're going to write, let's put in black here. You see, this will be sigma 3, 3. Now, here and here. This will be sigma 3, 2. You see, it's parallel to x2, and this is sigma 3, 1, because it's parallel to x1. So you have 9 components. Then you have a matrix. You see, sigma ij is equal, now, sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, sigma 2, 2, sigma 2, 3, sigma 3, 1, sigma 3, 2, and sigma 3, 3. That's This is a stress. You see the, now we can write, see, element of the stress tensor. You see? Or we see elements, we always use this word, components of the stress tensor. Sigma, you put here, this is the stress tensor. Now, or the element of the matrix sigma ij, as we did before. You see, I prefer to use components of the stress tensor or elements of the matrix sigma ij. You see, now don't forget, these are what we call surface forces associated with it. Don't forget that the dimension is force divided by area. See? Look, T, let's put Tij is force divided by area. See? That is stress. When we say stress, is force divided by area. Sigma, you see, is force divided by area. Okay? Now, don't forget that sigma j associated force by area, that's called contact forces. You see, or surface forces. See, a contact force. You see, never forget about surface force. For instance, this plane over here, you have, let's draw here this x1, x2, x3, okay? Just to follow there. Now, you see, for instance, this x2 direction, here we have sigma 2, this will be sigma 2, 3, because it's parallel to 3 over here, okay? And this will be sigma 2, 1, because this vector over here is parallel to x1x. Now, and this neighbor here, you see, look, this neighbor over here, you have to have, for the equilibrium, you have to have like this. So this will be sigma 2 in the opposite direction. You see? Now, and here, you see this vector over here, sigma 2, 3, you see? And this over here, you have to have, okay, to compensate this stress over here. Let's continue this, you see? You have to have this, you see? This plus this will be 0, because they are in contact, okay? And this one is be over there. So, you see, because it's a surface force, there's a continuum mechanics. They have a contact between the surface and that one. Like, for instance, let's see this one. You see, here on the central element, we will have here, look, x sigma 2. Now, here will be sigma 2, 3. You see this 3, and there sigma 2, 1. You see, because there's a face perpendicular to x2. Now on this face over here, you see, because in the equilibrium you have here sigma 2, and here you have sigma 2, 3, and here sigma 2, 1. You see? Because you see that they are surface force. They are in contact. You see this arrow here? Look, it's there. See? In the opposite direction. See? Now, this over here in the opposite direction, that one. And this one in opposite direction, that one. You see? So, when we analyze an element, now, we analyze this element, see? Now, you know now that on the sixth surface, if you have sigma 3, 3 here, on the surface here, you have minus sigma 3, 3. Now, because this is a force by area, let's call this delta x1, delta x3, and this here, delta x2. You see, look, this x2 axis, you see x2 axis. This is x1, this is x1, and this is x3. So if you multiply by the area, the x1, delta x3, that's the force. The same here, delta x1, delta x2. Let's put delta x1, x2, delta x1, x2. Because this area over here, you see, sigma 3, 3 is force divided by this area. And this area is delta x1, x2. Like, for instance, we have, suppose we have here, let's put here, tau or sigma 3. You see, this axis is parallel to x2, so that is sigma 3, 2. Here will be this way, so this will be sigma 3, 2. Now, the force is minus, let's see the area here. You see that delta x1, delta, this case, okay, delta x, this area over here is delta x1, delta x1, delta x2. This is delta x1, delta x2. Because this is stress, okay, is force divided by this area over here. See? Let's work on this one just to see what's going to happen. So this will be sigma, you see, this is x2 direction. So this will be sigma 2, now 2, 2, okay? Now here will be sigma 2, 1, because this x here is parallel to x1. And this will be sigma 2, 3, because it's parallel to x3. Now the force, you must multiply by this area over here. See, delta x1, delta x3. So this will be sigma 2, 2, delta x1, delta x3. Like sigma 2, 1, delta x1, delta x3. Because these are the stress is force divided by this area over here, okay? And this area is delta x1 and delta x3. See? Now we have to fill, okay, all these 6 surfaces, okay? Now let's apply Newton's second law on this. Newton's second law, the assumption is no motion. The element doesn't have any motion with respect to the inertial frame. So the acceleration with respect to the inertial frame actually is x1, x2, and x3. Let's put here x1, x2, x3. It will be 0. So Newton's second law, this is the net force that acts on this element is equal the mass dm times the acceleration with respect to the inertial frame. Let's put inertial frame. Now, since the inertial frame, the acceleration is 0, so the resultant, so the net force will be the surface force plus the body force has to be 0. So the Newton's second law. Now, I'll explain to you what I'm doing here. Look, we have on this element 6 plane surface. Now, each one has 3 components. So we have 18 components just to play with. Now let's split this in 3 parts. I will consider only x1 components. x1 components. So this will implies in 6 terms. Okay? 6 terms, because x1 components, 6 terms, x2 components plus 6, x3 plus 6. So this will add in this will be 18 terms. Plus 1 term is the body force. Now, for you to understand the picture, I split this element, okay, in 3 faces, the face here and the back surface. This is the front surface, this is the back surface. I will draw this element here for you to understand what I'm going to do. Now, let's consider this element here, all these 2 parts together. So let's do this. So this element here, okay, now, this element here, okay? Here's x1, let's put this, x1 component. Okay, this face in which E1 is normal, the front face here, this will be sigma 1,1. Attention now, sigma 1,1 is not force. There's this force by area. So this area here, you see, this is delta x2 times delta x3. I'll write this later. Now, we already had the first terms in the x1 component, you see. Now, there is one on the back surface there. This is sigma 1,1. You keep in the opposite direction, you see. Now, this one, okay, the x1 direction. And there is another one there, you see, that's the back one, okay. This is sigma 1,1. Let's write here, sigma 1,1. And that right here, sigma 1,1. Now, let's find out more, okay, in which the components are in the x1 direction. Let's see this front surface, which is here, you see. Now, this surface over here is sigma 2,2, okay. I don't want sigma 2,2. I want the component, I want x1 component. Now, it's simple. This will be sigma 2,1. You see? On this is a front face. You see, this here will be sigma 2,1. Now, on the back surface, it's the same here, in the opposite direction, sigma 2,1. You see? Now, we already have 4. You see, 1, 2, 3, 4. We need 2 more. Let's consider this face over here. So, here is sigma 3,3. We don't want that. We want the component in the x1 direction. So this will be sigma 3,1. Now, on the bottom, it will be just the opposite. I just put here, okay? Now, sigma 3,1. Under the bottom here will be sigma 3, 1. Now we already have six terms, you see? The 6 here. But you know that the stress, it's not force. What is the force is the stress times area. Another point, you see, this is a point P over here, you see? Where is the point P there? Okay, look, there's the point P over here. You see, there's point P. Now, here's the point Q. Where's the point Q there? It's right here. You see, there's the point Q. You see, there's Q. You see? So, this is delta x2, this is delta x1, delta x3. Q is equal x1 plus delta x1, x2 plus delta x2 plus x3 by delta x3. You already did this element here. We already worked with it before, okay, under vector and tensor course. Now from here, let's obtain the forces. Again, sigma, the stress tensor, the stress components, they are not vector. They are vector by area. Now, then when you finish this, you just do for x2 components and x3 components, plus the body force. There is only one volume. So the body force in one term. So this combined with this, we have 19 terms. 18 for the surface forces and plus 1 for the body force. Okay, we have only one volume. Body force is not a contact force. Okay, there's 6 components, x1 component. This is attention, this is x1 component only. DFS and x1 component. You see, now this is sigma 1, 1 times the area. Okay, what is the area? The area is delta x2, delta x3 is over here. Where? At x1 plus delta x1. You see, there's a point Q. Now, minus x1, 1, delta x2, delta x3, located at x1, at point P. You see, this face here is at x1. Now, let's do the same with this here. So, this is sigma 2, 1, delta x2, delta x3, where? At x2 plus delta x2. So, this is x2. You see, this area over here is at x2, and the front in this case, will be x2 plus delta x2, is this here. You see? Now, you see the arrow here, the direction is the same direction x1. That's why this is plus and this is minus, because why is minus? You see, because in the opposite direction of E1. Now the last 2 terms will be sigma 3, 1. You see, sigma 3, 1 times the area, because this is a force. What is the area? Delta x1, delta x2. That's the area over here, you see? That's the area. And plus, because the arrow here is the same arrow of x1. That is plus. Minus sigma 3, 1, delta x1, delta x2, located at x3. x3 is here, and this face over here is x3 plus delta x3. Now we will apply the derivative, the partial derivative. As you know, you see, this here is a partial derivative, this over here is a partial derivative, and this over here, we apply partial derivative. Now, let's put x1 here. Now, this is equal. Now, let's combine these 2 terms here. It will be partial derivative of sigma 1, delta x2, delta x3, with respect to x1, delta x1. Don't forget, you see, as I mentioned before in the videos there, you see, look, you have a function x plus delta x minus a function of x. This approximates to partial of this function with respect to x delta x. Don't forget partial derivative with respect to x, delta x. You also have y plus delta y. This is y, partial derivative with respect to y, delta y. So this is a partial derivative with respect to x1. So this is equal, you see, look, delta x2, delta x3 is constant. When I move from x1 to x1 plus delta x1. So here will be delta x2, delta x3, partial derivative sigma 1, 1 with respect to x1, delta x1. Don't forget this, you see, look, this is delta x, see, delta x. So this will be delta x1. Don't forget that. You see, partial derivative with respect to x1. Plus. Now I'll combine this two term over here. Delta x2, delta x3 is constant. In this case, let's see, there is something here. Sigma 1, delta x2, delta x3, sigma 1, 1, they're here. This sigma 2, 1, delta x1, delta x3, this is one over here, okay? This is one over here. See, because sigma 2, 1, the area is this area over here, see? So this delta x1, delta x3. Now, you see, plus, now the second term over here, that will be delta x1, delta x3, now partial of sigma 2, 1, with respect to x2, delta x2, don't forget that, you see, delta x2. Now, see, I combine this term, it's here. I combine these two, it's over here. Now, I need to apply the derivative on the third one. Plus, now, here, will be delta x1, delta x2 is constant. So, delta x1, delta x2 is constant. So, the partial derivative with respect to 3, 1, with respect to x3, you see, x3, don't forget, delta x3. Now you can see easily that this term, delta x1 is delta v. This term, delta x2 is delta v. Delta x1, delta x2 is delta v. So I can write that, you see, dfs1 will be, now I write down here, just easily, that I put partial sigma 1, 1 respect to x1 plus partial of sigma 2, 1 respect to x2 plus partial of sigma 3, 1 respect to x3 times delta v. Because delta v is delta x2, delta x1, delta x3. Now, you can see an interesting remark. Sigma is force by area. The variation of x1 is length. So, partial derivative of sigma with respect to x, this is force by volume. You see, because sigma, look at here, look. Sigma is force by area. Now, sigma of length will be force, length times area. Length times area is volume. So this is force by volume. Force by volume times volume is force. It's okay. You see? So, derivative of sigma with respect to a length, x1 or x2, is force by volume. Times delta v is force. You see, this is when you write, look, when you write partial derivative with respect to x, you see, this is an operator, okay? There is no unit. It's dimensionless. Now, x partial of respect to x, this is a variation of x. So, variation of x, the dimension is the same dimension of x, okay? Variation of something, okay? The same unit of something, okay? Variation of mass, you see, cannot be length. Variation of mass has to be mass. So variation of x is length. So that you see clearly here. Now we want to obtain DFS 2. Okay, 2. Now I can write down here using tensor notation. Look, don't forget our course is vector and tensor. So I will raise here. See, look, it'll be just fast and quickly I can write down like that. You see, look, you see here 1 1 2 2 3 3. So this will be a partial with respect to xj. You see, looks is 1 1 2 2. So this is sigma ji. Now you see, if I is equal 1, I just put 1 here. You see, 1 1 and 1. So this is I. Okay. Now if I develop for DFS2, I'm sure this will be partial respect to xj, the sun, sigma j 2 here. Okay, so I can write that the surface force I, let's put here, I will be now partial of sigma ji xj, attention now, dv in the volume, okay, because this is force. Now this element, as delta v goes to 0, so this delta v goes to 0, this is dv. So this is surface force at point P, you see, at point x1, x2, x3. Now if you want to work force by volume, you just take this dv out, okay? So this here, attention, this here is a vector. You see, this is a vector. Why is a vector? One free index. You see, this is a vector. Look, doing this is worthless to do for DFS2 and S3. You see, because I'm sure if I do that, I'll find out here too. And this is a summation. If for x3 component, this will be 3. So this is a vector. Okay. Why it's a vector? You see, one free index. See? Now, you see, I'll write down here. Let's put instead of doing this, I will repeat here. Okay, the same thing. Okay, I'll just do this. df is equal dfs plus, now here I'll write down like dm times b. dm times b, this is capital B. I just wrote here. Okay, this is dfb. Let's put here dfb. Okay, the body force is the mass. You see, a volume, it has a mass. Okay, I call dm. I just put dfb as dm times small b. Let's write down here using tensor notation. So dfi is equal, now we just did here, see, partial of sigma ji respect to xj, dv dV plus dm bi. Attention now, look, what is the free index? Is I. What is the free index here? Is I. This must be free index I. Now, it's common in elasticity, fluid mechanics, you work, instead of dm, you work with the density, mass density. I'll show you why, okay? Now, people in general, they work with the density without knowing what they are doing. See, but I will show why it's better to work with the mass density. Okay, it's called volumetric mass density. In general, in physics, you forget volumetric mass and just call density. The symbol is the Greek letter called ρ. ρ is defined as limit as delta V goes to 0 of delta M over delta V. You see, under mathematical viewpoint, that's okay. What do you mean physically by delta V going to 0? You see, look, you have anybody, you have space, okay? Molecular space. So delta V goes to 0 is dV, you see? Could be this here. So there is no mass, you see? Because there is some gaps between molecules, you see? So if you use the math definition, you write down dm over dv, you see? dm over dv is a math. That's why I like to use here delta v asterisk. Delta v asterisk is not as small volume as I want, but is some volume which contains some molecule inside there. Now we are going to use this definition, knowing this, dV is not as smaller as I want. You see, let's use this. You see, but knowing this here. Now, dm is rho dV. You see, I'm sorry, let's put rho dV. Okay, obviously rho is mass, unit of mass divided by volume. You see, mass by volume times volume is mass. Now let's substitute this over there. Now dfi, df, let's put, yes, dfi is equal, now partial derivative of sigma ji respect to xj dv plus, now dm is rho dv bi, this equals 0. You see, many books and videos, they just use rho without explaining clearly why you use the density and not the mass. It is because you can cancel dV over here. That's it. So this equation, this is not dFi anymore, because dFi is force. Now here actually is force divided by volume. You see? So when you write the elasticity equation, look at that. If you write the elasticity equation in a book, you see in a book, for instance, dFi is equal partial ji respect to xj plus rho bi. So you receive this. You you are studying a video or in a book, you see like that. For sure, this dFi is not the same on this lecture. This dFi is force by volume. You see? This here is force by volume. Do you remember? Look, look. Variation of sigma has the same unit as sigma. So, in the numerator is force divided by area, is length squared. Now, variation of x is L. You see, variation of x is length. Variation of length cannot be area, cannot be volume. So this here is force by volume, by L cubed. You see, force by L to the power 3. Okay? Likewise, this, you see, this here is mass by volume. You see, rho is mass by volume. This term over here must be force by volume, because it has to be equal to that one. You see? Now you have the equation, elasticity equation, involving the surface force by volume and the body force by volume. Here we see a brief review of the Newton's second law applied in this lecture. Now, here dFs plus dFp is equal to 0 because acceleration is 0. Now the body force is dmb. Attention, b is force by mass. Why? Because mass times force by mass is force. Now dFb rho dV, because dm, you see dm is rho dV. Now mass by volume times force by mass. So you cancel mass here, you cancel volume here, so this is force. Now you just wrote dFi in a vector form, you see, and the rho bi ei. So on tensor notation, you remember, you just take this ei here out and write down dFi divided by dV. This is force by volume. This is mass by volume times force by mass. So you cancel here. You see, it's force by volume. So this whole term here is force by volume. You see? Like this is force by volume, this is force by volume. So the equilibrium net force is equal to 0, you see? Now, the partial derivative of sigma ji with respect to xj plus rho bi is equal to 0. So don't forget this. This is force by volume, this is force by volume, force by volume. Okay? That's a brief review of this lecture.